Okay, let's continue our discussion. We were discussing about streaming stored video. So today we will finish discussion about streaming video and then also look at CDNs in brief. Okay, so last time we have seen how basically video is encoded. There are two ways of encoding: constant bitrate video and then variable bitrate video. In variable bitrate video, the encoding rate changes over time based on the spatial and the temporal variation in the content. So in general, the video is stored on a dedicated server after recording and then pre-processing. This is typically called as the video server. And from this video server over the internet, the clients play the video. There are different types of video applications that are used in internet. One is live video, wherein the playback, the recording is streamed in a continuous fashion while it is going on, and then while it is sent to the server, it is also being simultaneously played. Other one is on-demand video, where the videos are stored and then they are kept on dedicated servers, and a client can download the video completely over the internet and play it. The most popular one is what we are all familiar with. This is called as streaming video. So in streaming video, even though the video is stored offline and it is already available in a complete form, the playback can start while the file is still being fetched at the client end. So the client doesn't have to wait for the video to be downloaded completely. As it starts downloading the video, it can also start playing the video even before the video is completely downloaded. So this particular type of video is called as streaming video. So streaming basically refers to the process where an application can keep sending the data while the client or the consumer can consume it without waiting for the complete data to be present at the client side. There are several challenges that we have in the streaming application. The main challenge is that the server to client bandwidth, it tends to vary over time, particularly when you are using a wireless link or mobile network. The throughput fluctuations are very rapid and drastic, and it can be as low as few kilobits per second, and then it can go as high as few tens of megabits per second or hundreds of megabits per second. And then added to this, there are also network congestion levels that keep changing. So you can have congestion within the house when there are multiple devices trying to access the content over the internet over a Wi-Fi network, or it can happen because of the other users having or other users consuming data in the access network. The congestion can happen at the network core, and finally the congestion can also happen in the video server, where there are large number of users trying to access the video content from the server. Due to this congestion, which can happen anywhere across the network path, there can be packet losses. The packets can get delayed due to congestion, and this delay due to congestion makes the delay variable, random, and then it creates jitter in the packet arrival process, and this can pose significant challenges to the client as far as the video playback is concerned, and all this ultimately causes poor video playback at the client, which people also called as pure quality of experience. So in general, when we talk of streaming stored video, the video is recorded at a steady rate, and then it is sent to a server wherein it can be stored, and then the video is broken down into chunks, and these chunks are then fetched over the network. Okay, so when we stopped with the last class, one student asked, why do we use the other server here, which is shown as step 2. It could be for variety of reasons. So when you record a video and then send it, you do not tend to then generally stream it directly as it is. You might have to do compression. You might have to convert it from one format to other format. And more importantly, when you are doing this streaming stored video, you also have to break down the video into smaller chunks. You cannot send the video in as a sequence of bytes in a continuous manner. So we break down the video in smaller chunks and then store them on the server. It can be one server or it can be multiple servers. And then you have to also give unique identifiers for these chunks so that you can fetch these video chunks over the internet using a standard protocol like HTTP. So the video is also sent or transmitted from this video server at a fixed rate. But then assuming that there is no jitter, if the network delay is fixed, so we start getting these chunks after a fixed amount of time and in a periodic fashion. So the rate at which the packets are being sent from the server, it remains undisturbed at the client. You will get it at the same rate in the client, which makes it easy for the client to play back the video. The only thing that I was mentioning in the streaming application particularly is that the client is still playing out the early parts of the video while the server is sending the later parts of the video. This happens continuously and the client doesn't have to wait for the video to be received completely before it starts the playback. So the main challenges in this streaming stored video over the internet, typically we do it over HTTP nowadays. So we use browser and then an embedded player for playing the streaming video. And whenever the client is playing out, the timing at the client and the timing at the server must match. So that means, let us say if the chunks are supposed to be played at 0, 2, 4, something like this, or say 0, 2, 5, 7 and so on, whatever is the timing for the playout of the chunks as decided at the server should also remain same at the client. So the playout timing at the client and the server must match. Otherwise, you will have basically jitter as well as stalls. But because the network delays are variable, which causes jitter in the packet interarrival, so the client side has to counter this jitter using some mechanism. So one of the techniques that is deployed widely in the client side to avoid this jitter in the playback so that the playback can be continuous or it can be done in a timely manner with the same original timing as the original encoded video. Typically, the client starts buffering the content before it starts playing out. So this buffering, again, the initial buffering is a system parameter. So typically, most of the players do about 30 seconds to 1 minute of buffering before they start playing out. Even for the live, there is always some amount of buffering that is done, maybe 2 chunks or 4 chunks before which you start doing the playback. So this buffering at the client or this initial buffering of the data before it starts playback is what gives you a cushion for the jitter. So the jitter gets absorbed inside the client side buffer because when the packets come at variable times, they are stored in the buffer and then you start playing the packets at a steady rate. So the player doesn't or the user doesn't notice this jitter in the network during the playback. Then there are also, of course, other challenges like the client needs to interact with the server, maybe do a pause, fast forward or rewind, or seeking, which is jumping through the video, going to a particular playback time. All these are typically supported as a part of the typical client. And in addition to this, you don't, despite you being playing this video over HTTP over TCP, which is a reliable transport protocol, the packets can still be lost or retransmitted inside the network. TCP takes care of retransmission of the packets. So that means whenever there is a packet loss in the network, the end-to-end protocol takes care of retransmitting these packets to the client. So now the question is whether the client has sufficient time to wait for the retransmitted packet to be played, or the retransmitted packet arrives after the timing. If it arrives after the time expires, there is no point in keeping the packet, because video goes by strict timing sequence between the packets. So what essentially we do by this buffering at the client side, or the playout buffering at the client side, is that we try to absorb the variation in the network delay, which indirectly causes the jitter in the playback. And irrespective of the variation in the network delay, the client tries to play the segments at a steady rate. So as you can see here, the red line shows the original rate at which the packets are being transmitted. The black line is the one that is received at the client but before playback, and the blue line is what is done exactly at the playback. So playback rate you have to match with the transmission rate, and then the jitter is basically absorbed due to the buffering of the packets in your client side. So this buffer is always allocated by the client depending on what is the perceived network bandwidth fluctuations, and it can vary anything between, like I was mentioning, 30 seconds to 1 minute of content to be stored in the video before it is being played. And you will see that there are these stalls whenever you play video, and these stalls happen whenever you have no data in the buffer. So if your buffer becomes empty, then the playback stops until you again start get sufficient amount of data in the buffer. The client doesn't start playing back. Okay, so the protocol or the mechanism that is used for streaming stored video in most of the clients these days is what is popularly called as DASH. DASH stands for Dynamic Adaptive Streaming over HTTP, and you can see there are multiple words here apart from streaming over HTTP. You are using HTTP protocol for fetching the chunks between the browser and the video server. Apart from this, there are also two words which characterize the streaming behavior. One is dynamic and the other one is adaptive. We will see in a brief manner what this dynamic adaptive streaming does. The first thing is that in the server, you divide the video file into multiple chunks. Typically, these chunks are of equal playback duration. That means each chunk has sufficient content to play a video for say 2 minutes or 4 minutes or 6 minutes. The size of the chunk can vary based on the richness of the content, because it's a VBR video. The actual sizes in bytes, they can be anything between 1 megabyte to 5 megabytes for a 2-minute chunk. Each chunk is then encoded at multiple different rates. This is what YouTube you will be seeing as say 144p, 360p, 720p, and then 1080p. So each of these chunks can be represented in multiple rates. So like standard definition or high definition or ultra high definition, and these different rate encodings are again stored as different files. So essentially you have the video encoded in different rates and then chunked and stored. So each chunk can correspond to 2 degrees of freedom. One is the rate at which it is encoded, and the playback duration. So you store all these chunks as different files, and then these chunks can be replicated across different CDN nodes. They can be placed in caches, they can be placed inside the ISP and at different locations across the globe. So to locate these chunks from the corresponding CDN nodes or the servers, Dash creates a manifest file. It is a typical XML file which describes the video, gives the URLs for each of these different chunks. URL naturally gives you the location of the chunk. Now what client does is that it first fetches the manifest file over the network. So whenever you click a video, it takes you to the manifest file. You parse the manifest file and then you discover the architecture that is used for chunk breaking down of the chunks and the corresponding encoding rate. So once you have the manifest file, then the client starts estimating the server to client bandwidth. It does this in an in-band mechanism. That means while it is downloading the chunks, it also measures what is the bandwidth available between the server and the client. Based on this estimated end-to-end bandwidth, it tries to understand what is the rate at which it can play the video. So looking at the manifest file, it chooses the maximum coding rate that is sustainable for a given current bandwidth. So for example, if the current bandwidth is say 3 megabits per second, and then the playback rate that can be sustained with 3 megabits per second is say standard definition. So it picks up that particular representation of the video. Some of the clients support many coding rates, not just 4 or 5, very fine grained level. So based on this estimated server to client bandwidth as well as what is the coding rate of chunks, it tries to match these two. And this is a continuous process. It is dynamic and it also should adapt according to the network bandwidth, because the server to client bandwidth can keep changing based on the network congestion as well as based on the other signal characteristics. So every chunk, the client takes a decision what is the available bandwidth based on the historical data that it is collecting, and then it decides what should be the rate at which the chunks should be fetched, or what should be the encoding rate of the chunk that it needs to fetch in the subsequent cycles. So for every chunk, or say for every couple of chunks, this decision making is done. And this is a typical optimization problem where you are trying to match the encoding rate given the or given the estimated value of the server to client bandwidth. So the entire intelligence is located at the client. There is nothing that the server can do or tries to do about this. It is the client which estimates the network bandwidth, and it also decides when the next chunk has to be requested because it looks at the buffer. So let us say it is storing 30 seconds of video, and as it keeps getting depleted, it fetches new chunks. And the objective is that the buffer should not starve. That means the buffer should not become empty. At the same time, the buffer should not overflow unnecessarily, because one issue in the stored video streaming is that the user can always jump to different locations. So if you are systematically buffering and you are doing an overflow, then the user, when he skips to a different location, all the data that is there in the buffer, it is useless, right? So you'll have to flush out the buffer and then again start fetching freshly. Okay, so those of you who who have been watching this YouTube, the way it buffers, earlier days it was doing something called as progressive download. That means it keeps storing the video continuously in the buffer irrespective of what is the uh, bandwidth. But nowadays there is a fixed amount of buffer that is maintained, and because the bandwidth can keep changing, and if suppose the bandwidth improves, you can always get a higher resolution video at a later point of time. So instead of this continuous buffering, it does a periodic buffering for some amount of time and then takes a decision of what to fetch for every two chunks or three chunks at a time. So when to request a chunk, and then what encoding rate to request based on the available bandwidth, and from where to get these chunks. That is, if there are multiple replicas for this video, if there are multiple locations from where you can get, then you can also measure the end-to-end bandwidth based on the server where the video is located. So you might be getting better bandwidth from one server and less bandwidth from another server based on the server load. And this also can be a deciding factor. So when, what encoding rate, and then where to request this chunk, all this can be decided by the client. Okay, so streaming video essentially has three features. One is the encoding, the rate at which the video is encoded and stored in the infrastructure. Then dash is the algorithm that is used for intelligent adaptive streaming of the video chunks based on the network bandwidth that is estimated. Plus the buffer or playout buffering is used to nullify the jitter that is incurred due to the variation in the delay in the network. Okay, so any doubts in the streaming video part? Okay, if it's clear, then we will next discuss what is the content distribution network infrastructure that is used for delivering the content. So content distribution networks or CDNs handle essentially the challenge that we were discussing as how do we scale delivering content which could be videos or which could be resource intensive content like multimedia content to thousands or millions of users who are simultaneously trying to fetch the data from a server. So the problem here at hand is that if you have a single large server or a cluster of servers at a single location, it is not going to scale well, particularly when your users are distributed across the globe. So the users are from different countries and then they are connected to the server through different networks, ISPs. And the speed of these ISPs is also variable. The physical distances to your server is largely varying. So for example, if you have a server in India, then on one end you have users from San Francisco, and at the other end you may be having users from Tokyo or some location in Australia. So the distance itself is widely varying, and then you can also have large variation in the end-to-end bandwidth that you perceive at any given point of time. Apart from this, there are also these issues that if you have one server, be it one single server or a replicated cluster of servers, it is still a single point of failure. If it gets disconnected due to any issue with the ISP, you will not have the content available to the users. It becomes also a single point of network congestion, and then the path to clients can become very large based on where the clients are located. So this is a problem if you have a globally distributed user base and the content is located at one single place. So simply these old solutions of a server-centric approach, they do not scale to large number of users spread across the globe anymore. So what we do is that we replicate the content, we store multiple copies of this content at different locations, and these locations are geographically distributed across the globe, and then we tend to serve this content from the locations across the globe. So this is slightly different from simple replication. So in our replication, the objective is to simply improve the reliability. If one replica goes down, then you activate the other replica to serve the content. But here what we are talking of is we would like to parallelly serve the content across the globe and have some intelligence from where the content is being served to a particular user or a group of users from a location. So we try to address multiple things here. One is that we try to store the content in multiple replicas, and then we also try to serve the content from a replica which is closer to the user rather than serving it from a geographically farther location. So the basic objective of these CDNs is to push the servers into distinct access networks so that the servers are closer to the users. Closer in the sense that, geographically closer. So the propagation latency itself is going to be less because the servers are very close to the user. Plus, because it is there in the same access network or same ISP as the user is located, the ISP has a better control of over the network bandwidth, and you tend to get better bandwidth if the content is inside the ISP as compared to the content being located in a farther off location. So Akamai, the leading CDN company, as of 2020 has deployed about 3,25,000 servers in more than 135 countries and 1435 distinct ISPs to push the content as close to the user as possible. The other objective of the CDN networks is also to have, instead of having a big data center or big cluster of servers at one location or fewer location, you can have smaller number, maybe tens of these clusters in POPs. So POPs, as you are aware, these are exchange points where multiple ISPs are interconnected. So the idea is that if you place these content at a POP or internet exchange points, these are meeting points where traffic from different locations it meets. So if you put your content there, then you can serve to a larger set of users with a lower response time or access latency. This is the approach that is used by other CDN, which is Limelight networks. So they put lots of these smaller clusters of servers near these internet exchange points so that the content is served from locations closer to the ISP or operating ISPs. So in essence, what CDNs do is that they store copies of the content. Let us say some video file or a movie at different locations, different CDN nodes, and then the user can fetch the content from any of these locations or any of the replicas. Uh, when the subscriber requests the content, the service provider only gives the manifest file instead of the actual video. The manifest file then redirects the client to the appropriate replica. So for each client, the manifest file is different. The manifest file can be tailored so that the content is picked up from a server or a replica which is very close to the user. So this is how, when you are trying to search for a movie from the client, the Netflix only gives you the manifest file, and with this manifest file, then the client can basically fetch the content from any closer location. Okay, so there are a few things here, a few questions which might occur to you. First thing is that how do I know which is the closer replica, which is the closest location? In the earlier days, it was done based on the geolocation, based on the IP address. You know roughly where is the particular IP address? Is it in India or is it in Japan or some place? And based on the location of the IP address, you might choose the appropriate replica. You means the content service provider would redirect you to the appropriate replica. That is one option. The other option is that if you are trying to fetch the content from one of the replica, then that particular location might redirect you to a different location. You can use URL redirection or IP redirection, any of these techniques, or even use DNS effectively to give a different IP every time you try to fetch the video. So each time, let us say a user from India fetches, for some users, the content might be served from a server in India. Then if the server is loaded, then you might try to fetch it from a location in Singapore or something like that. So there are multiple factors here which can be considered: load on the servers, location of the client, location of the server, distance between them, the network bandwidth that is there between these two locations, client and the server locations, the ISP in which the client is located. So all these factors can be considered to serve the content in an intelligent manner from nearby replica or from a replica which maximizes the end-to-end throughput for the given playback or file. Okay, so for all this, what the CDNs essentially try to do is they try to deliver the content over the top, which is what is called as OTT. Now this OTT is a very popular term. We call it as OTT video or OTT channels and OTT content. So OTT content is all about not using the underlying client server infrastructure or underlying routing architecture in the internet for serving the content, but instead have your own mechanism for distributing the content across the network and also redirecting the clients to appropriate locations. So essentially you will have this kind of architecture where the servers are not physically connected, but they are interconnected with each other using an overlay. You are using the internet only for the basic packet transfer between the end machines, but rest of it like the routing and the name resolution, then identifying the replica which is closer to the user, all these your basic internet protocols they cannot support. So what you do is that you have your own routing framework or your own DNS framework to support better identification of the content closer to the user. So when you serve this content over a CDN or over the top, you are trying to essentially cope with the congestion in the internet as perceived from the edge nodes. So there are multiple issues here. One is, since you have decided to have multiple replicas, which content to place in which CDN node, you can have something like popularity. You can have this decision done based on the historical access patterns, based on the user base for a particular video or a particular language. So based on the specifics of the content, you can then decide where to place this content at which particular node to place. Then how do you route the content across these overlays? Of course, there is also issue of cache coherence because these are all mirrors. So you need to have consistent information across these mirrors. If it's static, then it's not a big issue. But then if you have dynamically varying content, then CDNs also have to take care of consistent consistent update mechanism for data across these CDN nodes. Then routing this content in the overlay, you essentially have kind of a semi-permanent TCP connections between these CDN nodes, and then you can route the content from one overlay node to the other overlay node. You are not using the basic IP routing protocol for this, but you are having your own routing across the relays of your CDN network. And then there are also decision making. You also need to decide on which node to use which particular type of content and at what rate you want to fetch the content. All these are decided with an intelligence which is placed within the content distribution network. So DNS is also used for a lot of these tasks by CDNs. As I was mentioning, DNS can do load balancing. So if you have multiple IP addresses corresponding to a domain name, you can rotate the IP addresses in a round robin fashion with your own authoritative DNS. So when the query comes to the authoritative DNS, the CDN's DNS can then take a decision on what is the IP from which the content needs to be served. Accordingly, you can manipulate the DNS resolutions so that the client is redirected to a particular replica at a given point of time based on the load and other conditions. So you also have kind of a monitoring infrastructure for the CDN which takes care of the load of the servers, the number of users that a server is serving currently, the end-to-end bandwidth perceived between the server and the client at a given point of time. All these are also collected at a central location wherein the decision making is done for all these steps, like where the content has to be served from and at what rate and so on. Okay, so just to summarize, to give you an example, so nowadays most of the content, as you might be aware, if you look at the browser, transcripts, you will be able to notice this. So most of the popular sites like CNN or any other major news channel, they will change their URLs to the CDN's URLs. So for example, if the video is, initially the video must be represented with a domain name, say netcinema.com. So when you try to click on the video, which initially is supposed to resolve for netcinema.com, the video might actually be stored on a CDN. So that CDN maybe say kingcdn.com. So the first resolution for netcinema.com will essentially return a canonical name for the URL or for the resource, pointing you to another domain which is say kingcdn.com. Now when you try to resolve this kingcdn.com, you are essentially sent to the DNS system maintained by the kingcdn. So this could be, a customized DNS version which tries to do load balancing and the other functions that I was talking of. All this can be implemented with the kingcdn's DNS system. So then it will basically take you to kingcdn's authoritative DNS, which will then point you to the actual video replica from where the client needs to fetch the content, which is then fetched via the HTTP protocol. So the CDN content is all essentially changed. The domain name or the URLs are all changed to reflect the CDN's names. And then these CDN's names are resolved with either the public DNS or with the private DNS systems maintained by the CDN. And then they can take you to the correct replica or the appropriate replica from where the content needs to be served. So Netflix also does similar things. All the movie portals like Netflix, Amazon Prime, all of them, they have a registration accounting server where they manage the account. So you browse the videos in the Netflix portal, but once you click a particular video, the playback starts with the manifest file being sent to the client. The manifest file then contains the exact locations of the video pieces, and this could be present in multiple CDN servers, and these CDN servers could then be changing based on the load of the CDN server as well as the location of the client. So from the same city, if you are playing a video from a mobile device or if you are playing it from a desktop or a laptop device, the CDN server which is used for giving the content, it can be different. So there are dedicated servers nowadays for mobile devices, and there are again dedicated servers for the desktop and other wired devices. Okay, so this is about CDNs. I will just stop with a discussion of the basics of this socket programming. So how do we interface between the applications and the transport layer? So as I was mentioning, all these applications run on these overlay networks. These overlays are created essentially with semi-permanent TCP connections. So you have a kind of a pipe or an end-to-end connection between the CDN servers and the DNS servers in form of TCP connections. And all the packets like the routing packets or the DNS resolution packets, all of them are tunneled or they are encapsulated as TCP packets and sent over these semi-permanent TCP connections. So lots of these applications nowadays, they only use the native IP or the internet for doing the packet transfer at the network layer. But beyond that, the transport layer and the application layer functions, all of them are done in an individual or in a customized fashion for getting better performance as compared to using the standard transport or the application layer protocols. So in the lab, I think in the next assignment, you would also be learning how to do the socket programming. How do you build client server applications or for that matter, peer-to-peer applications? Because peer-to-peer application is just an application that functions or has the role of both client and server in a single device. So you will still need to build a client application as well as the server application executing on the same device. And all these applications communicate basically with what are called as sockets. So you're also introduced to this notion of the sockets in the operating system as an IPC mechanism. So two application processes they tend to communicate with each other using this notion of sockets. So a socket is essentially a door between the application process and the end-to-end transport protocol. In internet or in the TCP/IP architecture, we have two types of sockets corresponding to two types of transport services. One is a connection-oriented transport service, and the other one is a connectionless transport service. So in the connection-oriented transport, we use TCP socket, or we use TCP at the transport layer, whereas in the connectionless paradigm or in the connectionless approach of communication, we use UDP. So based on the type of socket that we use, the the communication paradigm is different. The connectionless paradigm gives you an unreliable datagram delivery service. It doesn't give you any more features than what is already given in the network layer. So just like the way IP packets can be lost in the network, the same way UDP segments also can be lost over the network. It doesn't ensure reliable delivery of the datagrams. Only additional function that UDP gives you is that it helps you multiplex multiple applications on the same transport protocol. So you can have multiple UDP applications like DNS or say any other application which can run simultaneously over the UDP. Whereas TCP gives you reliable delivery service, and it can give you the byte stream oriented approach. So it takes care of delivery of each byte, and then also does the acknowledgement and retransmission. You will study all these details of these protocols in the transport layer when we discuss this. So in general, an application works either as a client or the server. The client say can, let us say we take an example where the client reads a line of characters, say from the keyboard, and sends it as some packets to the server. The server receives this data and then converts these characters to uppercase and then sends it back to the client. So client receives the modified data and displays this on its screen. So this is a simple application which involves bidirectional communication. The client is basically sending a string of characters typed from the keyboard to the server. The server gets these characters and converts the case, and then again sends it back to the client. So client receives this data and displays on its screen. So you have a pair of communicating sockets here. One is from the client to the server, and the other one is from the server to the client. So in case of UDP, we do not establish any connection between the client and the server. So whenever you have some data to send, either the client or the server, it doesn't require any acknowledgement from the server. It simply starts sending the data out. So whenever the sender has to send some data to the receiver, it attaches the destination IP address and what is called as the port number in each packet. Port number is a unique identifier that identifies the sockets. So you send this data to the destination IP address and port number, and receiver extracts the sender's IP address and port number from the received packet. So in this case, because it's an unreliable data transfer mechanism, the transmitted data may be lost or received out of order. So from the application viewpoint, the UDP doesn't give any better transfer than IP. And so it is the responsibility of the application to take care of reliability aspect of the UDP transport. So there are methods to create these sockets. Depending on what programming language you are using, the actual method might vary. But in general, the structure is to create a socket. When you invoke this command creating the socket, you are essentially creating a door through which your application can interact with the transport layer. And whenever you have to send a datagram, you send the datagram with the server IP address and the port number via this socket, and it goes to the other end. Again, the server application reads the data from the server socket, writes the reply to server socket specifying the client address and the port number, and then the client reads this datagram from the client socket, and then it can stop the process. So each time data is written into the socket or read from the socket, you are essentially demultiplexing or identifying the datagram to the correct socket with the IP address and the port number. In case of TCP, because there is reliable data delivery aspect involved, there is some handshaking that is required. So you need to set up the sequence numbers, acknowledgement numbers, and you need to maintain some state information to basically make sure that the packets are received in correct order and whether all the packets are being received or not. So simple constructs like the packets need to be given some sequence number, then you have to check whether all the sequence numbers are received or not. Whatever is missing, they have to be requested again from the sender. So all this extra bookkeeping has to be done by the client as well as the server. So for TCP protocol, before the data transfer is done, the client first tries to set up a connection with the server. So for this, the server process must first be executed and it must be listening. That means it has created a socket through which the client can start sending data. So the client connects to the server by creating the TCP socket, and TCP socket is identified with the pair of IP addresses, source and destination IP addresses, and source and destination port numbers. And when the client creates a socket, it establishes a connection to the server TCP, and the server side, it also creates a new socket for each client and maintains this socket as long as the client is active or as long as the client is expected to send some data. So explicitly, the sockets have to be released once the data transfer is done. Okay, so more on this later when you discuss this transport layer protocol. But the main difference between these two sockets is that one socket takes care of the data delivery in the correct sequence. So if there is any packet loss inside the network, the socket itself will not let you process the packets that are received out of order. Whereas in the other case, whatever the socket receives, the application can read the data directly from the socket without any checks in place. Again, the sequence is same. So the server creates a socket and waits for incoming connection request from the client. The client creates a socket and then sets up the TCP connection, after which it sends a request for reading or writing. And then whatever request is sent to the server, it is read, processed, and then the reply is sent back. So for every data or every byte that is sent from the client to the server or vice versa, there are also acknowledgements that are exchanged. So these acknowledgements will tell whether the data is received correctly or not, and any missing data will not be acknowledged, and the corresponding other party, the sender party, has to take care of retransmitting the data, and this is how the reliability is ensured for the application. So applications basically which use TCP, they do not have to worry about whether the data is done in a reliable manner or not. Whereas if you are using UDP, then the data has to be, the application layer has to take care of the reliability aspects. Okay. Yeah, so we'll stop here.